Sound is confirmed to be good. What we what we covered was Pinhole Camera, which is sort of geometric optics in a sense, roughly a simple model of algebraic projective geometry and the concept of center of projection. So this is kind of the Renaissance idea of projection and projective geometry. So that was a simple spatial arrangement of imaging. And in the second lab, we looked at individual pixels. What does a pixel in a camera measure? So we looked at comparametric equations, basically chapter 4 of the textbook, neatly summarized in a fun little lab with a photocell to make a 1-pixel camera to understand what a camera really measures by concentrating on only 1 pixel of the camera, what it measures. So we go from lab 1, which says what a camera is, to lab 2 that says what a camera measures. And in lab 2, what a camera measures, we had concepts like comparametric equation and concepts like quantographic theory. We had the notion. So I kind of want everybody to understand these concepts like infinitesimal, a lot of these general ideas, relationship between images, the trigonometric identities, in relation between the images of lab 1, and kind of introducing the concept, which was then again revisited in lab 4. And so lab 1 and lab 4 really tell us what camera spatially measures. Lab 3 was superposimetrics, chapter 5 of the textbook. So lab 2 is chapter 4, lab 3 is chapter 5, and lab 4 is chapter 6 of the textbook. So at least for those labs, if you just add the numeral 2 to the lab number, it points to the chapter of the book. So lab 2, add 2 to that, and that puts you to chapter 4. Lab 3, add 2 to that, puts you to chapter 5. Lab 4, add the numeral 2 to that, and that puts you to chapter 6 of the textbook. Lab 5 is active vision, which is a common topic nowadays with self-driving cars and LiDAR and computer vision and everything like that. So lab 5 was very important because it's an introduction to vision and active vision. And in particular, also water HCI. What I did is I added the afternoon section, the video for the afternoon section of water HCI. I added it to the ECE516 playlist because I think it's relevant. It is in the playlist there now. Water HCI, water human computer interface, is relevant. The afternoon section, at least some of the talks were on intelligent image processing, so there were some topics there that overlap quite strongly, so I think those topics are relevant to us. And then I also added that Borders Crossing Cyborgs lecture. The border crossing philosophy of cyborg technology says what's the border or boundary between environment and environment. So what is the boundary between the environment and the environment? So those concepts we should all know. Everyone should know the ideas of environmentalism, what we mean by environment or vessel, the boundary between us and what's around us. That's kind of important when we talk about wearable or implantable technology, and just a general taxonomy of technologies, surveillance, what's the difference kind of thing? How are these concepts defined and overlap? In the notion of comparametrics, so lab 1 with the photocell experiment, one of my favorite pieces of apparatus is that thing that we built, self-operating comparametric equation solver. So I explained what that was and how it works. And it basically, it solves the comparametric equation by moving across, the idea of infinitesimals. I think everybody needs to understand that. We had Adnan give a guest lecture on infinitesimals and the relationship between quantum field theory and comparametric equations. This is an example of an infinitesimal radially symmetric light source. All the lights are equidistant from the center, so they fall equally on the photocell. And then there is one that's switched on, or a set of them. In this case, they're in groups, so one set's switched on. So there's an idea that there's a certain number of lights, certain ones that switch on. That's an important concept. I talked a lot about photoresistors and photodetectors and photosensors, and even this apparatus. I took a simple photographic light and I rewired it. Originally, it was you could switch the left or right half, so for groups of them you could switch on, but I rewired it so that one switch controls just one of the lights. And I actually put 2 plugs on it so that I can remotely control it by powering just all of the lights except one, or just that one. So now with that capacity, we can do incremental or infinitesimal operations on lighting, on quantity of light. And infinitesimal is really the idea of infinitesimals and comparametrics. The apparatus has a slide on there and moves either a photocell or a light closer to either a light or a photocell. Whichever one's moving versus the other one doesn't matter a whole lot. I want everybody to understand these concepts. And in fact, if any of you have questions that you think are relevant for the exam, please let me know. So I would welcome, every year I say this, I welcome from the students contributions of any questions, because I might use them. So if you have a clever kind of thing that you think might test some aspect of this course, send it to me. Maybe you'll see it on the exam, or a modified version of it. So I love to get input from the class on possible exam questions. So give me some grist to work with. I'm kind of currently playing around with a few different ideas. I'm thinking of some kind of a slide thing that moves, like we did that machine that I showed. We built that machine that solves comparametric equations mechanically by turning the light on and off rapidly as it moved. Remember, we had 2 lights. You could turn one of them, but one stays on all the time and the other turns on and off, and then it zzz, it goes closer and closer and closer, or further and further apart. In a feedback loop system that comparametrically unwraps or unrolls or unravels comparametric equation. And so I was hoping that everybody understands that, because I thought that's a really cool thing. I was thinking, okay, could we make a fun, clever little version of that experiment, maybe that uses an XY plotter, so it can move in 2 different dimensions. The key element of all of this is zerometric knowledge. So what makes comparametric equations so powerful is they operate under the zerometric knowledge concept. So you don't need a ruler, you don't need to know how far away you are, you don't need any measuring instruments. So it's done by comparison. So therefore, it allows you to sense things that couldn't otherwise be measured. So that's a very powerful concept, being able to measure or sense things that could not otherwise be measured or sensed. So that's one thing that I wanted to cover on. I've got lots and lots of photoresistors here, and I could even collect some data from some of these photoresistors. I remember I just kind of went and bought at least one of almost every photocell I could think of, in existence. So I got this huge database of photocells. And that would be a lot of fun to do something with that. Make a really good exam question to roll that in there somehow, perhaps. Still trying to think of ideas. Send me any ideas you have, but take a look at this stash of photocells that I've got. This massive collection here. Got to do something with them, like maybe turn it into some kind of exam question, but there's all of these different photocells. And we could build like a parametric database of photocells. The exam is generally open book type X or whatever you call it, where you bring your textbook. There it is, photoresistors. Photocell, cadmium sulfide cell, CDS cell, or light-dependent resistor, LDR, seems to be a new modern terminology for it. It's interesting how the names of things change over the years, but the things themselves stay the same for a lot longer. So now, which is a pretty good term actually, LDR, light-dependent resistor. Resistor that changes its resistance based on the amount of light that falls upon it. And of course, that forms the basis for all kinds of amplifiers and things like that. Like a nice little experiment that we used to sometimes do is to take a triac and make a light dimmer, which varies the firing angle of the triac, varies the duty cycle, how long it's on, based on a resistor setting. And then if you put a photocell there, then of course you've got an amplifier because light falls on the photocell and then controls a much bigger light. So then we can create fun sort of feedback amplification type things with that. And that forms the basis for a lot of those nice sort of video feedback experiments to measure camera valence flux. So we talked a little bit about that. Give me some ideas on quantographic theory. So quantographic theory says that we want to make our graphs, what is a graph, for example? So I defined in one of my lectures, I defined what a graph is a locus of points for which it's a confluence of truth simultaneously, that the tick mark on the x-axis, let's say, equals the label of the x-axis, while at the same time the corresponding tick mark on the y-axis equals the label of the y-axis. So in this way, if we're measuring resistance, let's say, and we had a graph that was voltage across, amperage up here, as we increase the voltage, the amperage increases for a given resistor. If we had, say, a 1 ohm resistor, if we put 1 volt across it, 1 amp flows through. And if we put 2 volts across it, 2 amps flows. And so we could have the slope. Actually, if we put voltage on this axis and amperage on this axis, then the slope would be the voltage divided by the amperage, which is the resistance. So that would be an example of a simple relationship. We could say make that quantographically correct. So is this quantographically correct? So I've got voltage here, and I might have 1 volt, 2 volts, 3 volts. And over here I might have, or I am, let's say, I'll put amps across the slope as the resistance, otherwise the slope will be the conductance. So if we put amps across and volts up, then it's 1 volt, 2 volts, 3 volts. And here we got 1 amp, 2 amps, 3 amps, and so on, and then the slope here. And if it was like a 2 ohm resistor, then it would be twice as much slope, meaning that the slope is 2 volts per amp. And so that simply means that the voltage across the resistor is more when there's 1 amp going through it. It's got 2 volts across it if it's a 2 ohm resistor. So we could try to make that quantographically correct versus not quantographically correct. So what we can do then is take, say, the cross axis and divide both sides of the equation by amps to get rid of the units on the tick marks of the graph and put the units into the axis label. Then it becomes amperage per amp and voltage per volt. So those ideas are simple and universal. So I want everybody in this course to learn the beauty and the wonder of the very simple universal truths, which you do find that smart people understand simple universal truths. And so hopefully this course will make you smarter and bring to light some of these simple universal truths, like quantograph theory. So a good exam question would be, correct the following tables and graphs, because quantograph theory also applies to tables. Make the following graphs and tables quantographically correct. That would be a fun little question. We could have some kind of a system with lighting, light structure, light rail, something that's moving across, some kind of playing around with some ideas, like saying, okay, well, what if we had a photocell moving, say it can move further or closer to a pair of light sources or a number of light sources. Or maybe we have a two-dimensional spatialization to generalize that comparametric equation solving machine into a superposimetric equation solving machine. We could build a superposimetric equation solver, piece of hardware that solves superposimetric equations. Maybe we've got a light source up here and another one over here, and then we can move closer to this one versus that one, or find loci of points of equal distance from the light source without measuring distance. We simply move around until we find that the resistance is the same value. So we have photo cell with a resistance meter on it. We can ask, what we can move while keeping the resistance the same, perhaps. So that would be a fun little experiment. Another thing that we could do is we could build some kind of a movement device for panoramic imaging and sensing. Like we had examples of, well, okay, what is type 1 panorama? What is a type 2 panorama? How do I get the different types of panoramas to coalesce or to line up with a camera that's moving along? So we've got the prescribed movement of the camera can be parallel to the subject matter. Say the camera moves. If the subject matter is planar, then arbitrary camera movement leaves those images in the same orbit of the projective group of coordinate transformation. So I want everybody to understand video orbits, which is chapter 6. So try to really get a good understanding. I think everybody, I saw a lot of people had a good, solid understanding of the concepts in chapter 6. I saw some good examples through the Panoramics lab to have fun and play a little bit, have some fun and play with the rules of algebraic projective geometry. What if I was in a corner like this between these two walls that run at 90 degrees to one another? There's a door here and a mirror on the back of one of the doors. And then at right angles to that, it'd be easier to see there. At right angles to that door, there's a row of cathode ray oscillographs that are fairly planar. So this would be a good little corner to shoot something. We could have a camera that slides along here and then maybe stops and then turns 90 degrees and then continues along this wall. That would be a good example of a type 3 panorama. I could ask you even, what types of panoramas these are, various examples, and try to understand the situation. And what, from a practical point of view, what you can do with each of those types of panoramas. So those would be a good exam question type scenario. Another possibility is we talked about what a camera measures in terms of aperture and settings, like what do those mean, f-stops. We went through that a little bit, how much light's coming into the camera. Those are things that everybody should know fundamentally. Very simple fundamental things that you'd get asked in a job interview if you're trying to do something for imaging or intelligent image processing. We did a little bit of, the signal processing, image processing, that sort of thing. Also, the 5 labs, I think, were pretty much, everybody's up to date. We've graded them, they're all on Quarkus now. Check on Quarkus to make sure your grades are accounted for. If for some reason we missed your lab, let us know. So if there's something that wasn't graded, so if there's a 0 entry in there, like because you didn't submit it or whatever, let us know, because maybe if we didn't receive the message or the email or the link or whatever it was that was sent, let us know so that we can correct it as early as possible, so that Quarkus is up to date. There should be 5 labs. And of those 5 labs, there should be equal weighting of each of those 5 labs. So you'll have, each of them is out of 10. So your total is out of 50. And of course, some of you did really well on some labs. So it's actually possible to get more than 10 out of 10 on the lab and carry forward a high average. So we do sometimes see in this course some high grades from students who are switched on and do something really nice. Is there I don't have my grades for the last 3. Oh, so are those grades not posted? Can you guys chat me back if you see what's on Quarkus? Does everybody have like 5 grades in there for their labs, or is Quarkus dragging? Does it need to push? I'm a GitLab user. I wish they used GitLab for the grading instead of Quarkus, because GitLab, everybody knows how to use GitLab. You just click onto the repo, enter your grades, and then push it in. But I see only the first 2 are posted. So maybe our TAs can help us figure out how to push what's entered into Quarkus. Normally just click on CI/CD or whatever it is on the Git. And then when you click on CI/CD, it goes to pipelines. And then when you click on pipelines, it goes to passed. It checks to show that it's passed. So that's what somebody is, I should suggest that they enter the grades using GitLab. But anyway, I don't know. Everybody wants to keep changing the software every year. We had Quarkus now. It used to be something else. And before that, it was something else that keeps changing. So nobody quite, every time we try to learn how to use it, it switches to something else. So maybe I'll ask the TAs to get in there and see if those results need to be pushed forward. So, yeah, we can also have a bit of an open discussion for a few minutes. I'll save a little bit of time at the end to show that NASI, because I think everybody would enjoy ending the course with a little bit of the sounds of a hydraulophone, which is an example of a water-human computer interface, or water-human technology. I guess we think of computers or machines in the wide sense of technology, like a pipe organ is a machine. It computes the sound using Fourier series. If you look at how organ pipes are made, there's little holes drilled in the pipe in various places to cancel out certain harmonics, or little shaping of the pipe to emphasize certain harmonics in the Fourier series. So pipe organ is a pneumatic Fourier synthesis machine of sorts. And so what you see is the sculpting of the sound using the the shape of pipe to impart a certain Fourier series. And in fact, many of the pipes have, like there's Vox Humana pipes, which try to emulate the human voice using additive Fourier synthesis with pipes, which have air blowing through them, and the vibrations of the air will attempt to simulate various instruments. So you have the whole orchestra there being synthesized or simulated computationally, pneumatic computation, doing computation with compressed air, which is kind of fun. So that's an example of a human-computer interface that's not necessarily electrical, but it's still computation in the sort of analog computers, mechanical computation. So there's lots of different ways to do computation, and we can sort of really generalize and understand that. So let's have a bit of discussion, maybe. If anybody has questions, or throw me some questions for like suggested exam. Anybody have anything that they wanted to see covered? Have we missed anything in the course? Oh, when and where will the exam be held? Now, there's a rough approximate schedule for the exam, which is, let me see if I can just quickly look at that. And you have to check regularly because it's tentative. So it can change, so don't book your travel. So I see tentative here. BA 1190. So Monday, April 25th, 6:30 p.m., BA 1190, that's tentative. Usually these are tentative, so don't book travel during exam period. So what I would suggest is to check regularly. So the 25th, so that gives you now, it gives you about, not quite 2 weeks, a bit more than 1 week. 1 week, 7 days, 8, 9, 10, 11 days. So maybe about 10 days, given today's half over. So about 10 days to prep. So not a lot of time. So you want to use that time productively and effectively. And yeah, feel free to ask me any questions too over exam period. I'll be around, obviously, so I can jump on a Jitsi. I'm happy to jump on another Jitsi and talk, individually answer questions or go through things or discuss anything if any of you want to get on a Jitsi. And it'll be fun to meet up in person on if it's going to be on the 25th, unless they change that. It'll be fun, or whenever it is, it'll be fun to meet up in person and see many of you for the first time and say hello. And hopefully we'll meet up. And if any of you want to join meet up, we're gonna, some of us at the Swim OP group are probably gonna go for a swim on Sunday if anyone wants to join us and meet up at the beach or something for a little while. Welcome to join us. We'll probably be around. We'll be around anyway. I don't plan on traveling anywhere for the next little while, so we'll all be around. in Canada, Toronto area for quite a while. And yeah, any other questions? Oh yeah, open book means only allow textbook or other paper source. Yeah, open book means your own notebooks, papers. What we usually, like, it has to be done locally, so nothing to interact with the outside world. So certainly, you know, your own notepads and papers. And usually what I do is I write everything down. Like, it takes a long time to search through the whole textbook. So you could usually I'll bring in a copy of the textbook all annotated with sticky notes or whatever. But usually what I try to do is write down my own interpretation of the textbook in a summary of 2 or 3 pages of just handwritten notes. That'll help a lot to write down. Like, I would go through and watch the videos again from the class, watch all the videos, maybe speed them up 2 times on YouTube or whatever, and go through and watch them and mark time codes where interesting things are, and then try and write down summary, like, you know, write down key findings or key summary. You know, don't write down every single equation, but just write down your key insights and try to distill it down to insights for you. Now, your notes become very personal, because if you just got notes from someone else, they're not going to help you that much. If someone else summarized it and you grab, like, this is what I found. If you make a cheat sheet, a summary sheet, I guess we'd call it, because it's not really cheating, but a summary sheet, it'll be personal because it'll be your own memory of how you collected the summary. If I were to copy someone else's summary sheet, it wouldn't help me a lot, because it's not how I came into it. We all learn things differently. This is what Marvin Minsky said, is that we learn best things we already know. You have to already know something to learn it, so it's a very incremental process. And so you're going to build your own knowledge base, and the crib sheet or the summary sheet is an index to your own mind, because you built it yourself. So you have your own way of internalizing that knowledge, and that'll be the sort of summary of it. So you take the book, and then, you know, go by chapters. You know, go. I mean, the core essence of the book is chapters 4, 5, and 6. More or less the core things that to summarize. The other chapters are more or less conceptual. Like, once you've read them, you know, it's just like a little bit of common sense, more or less. Some radar stuff mentioned in chapter 2 and everything, but you can summarize that pretty quickly. I would make sure you listen to the talk on radar and everything, like the radar equation, 1 over r to the 4th and everything. Make sure you understand all that stuff and have a deep intuitive understanding of it, because that'll help you. But more or less, you want to you could go by chapter. Like, you could say, okay, I'm going to make a summary of comparametrics, and then write that down on a sheet. Comparametrics summarized on this sheet. You could make another sheet. This is how I would do it if I were studying. I would have maybe 1 sheet to summarize everything there is to know about comparametric equations. I'd have another sheet to summarize everything there is about superposimetrics. Another sheet to summarize everything about video orbit spatialization of cameras. And then maybe a couple more sheets to just summarize general concepts that cut across some of those different things, like, you know, the aperture of a camera, the f-stops, all the kind of knowledge that we acquired in the course. And then maybe loose concepts like active vision, sequential wave, and printing machine, and so on. And make these summaries, make these summary sheets. And then if you build your own little workbook that summarizes everything, you'll start to know your way around it and make connections between some things and other things. So try to make cross links whenever you can. Say, okay, what is the relationship between superposimetrics and comparametrics? Obviously, comparametrics is a special case. of superposimetrics. But how do those two relate? And how would you understand that relationship? Because that lateral thinking will give you the power. What I really want to teach you is how to think laterally, how to think creatively, how to make connections between disparate concepts, between one discipline and another discipline. So I'm hoping that you'll develop deep knowledge in those ways. So I hope I've answered that question from Shishong Gao. Anybody else have another question? And then what I'll close out with is just a fun little extra with that Nessie hydraulophone, which I've set up on the table here. So I have a clear acrylic basin on my chalkboard there. You can see it here. And I'll dial this down a little bit, gain this down a hair here. So what we see here is there's a clear acrylic basin with water in that basin. And there's a pump there on the left that pumps water into that pipe organ. And the water flows through the finger hole, into the finger holes. And when you obstruct the finger hole a little bit, there's an underwater whistle that is at the side discharge of a small opening. So normally the water flows through and goes right out the finger hole. But when you block it from the finger hole and stop it from coming out the finger hole, it pushes the water through an underwater whistle, which is fairly hard for the water to get through. So it would rather go out the hole, the finger hole. But if you block the finger hole so it can't get out the finger hole, it has nowhere else to go but out through that underwater whistle. And so that each of those separate 12 underwater whistles operate separately, so that one can operate at the same time as another one can operate. So it's like a pipe organ. It can play multiple notes at the same time, kind of like a woodwind instrument, like a flute, but it can play more than one note simultaneously. That water then goes out into the basin and lands in the basin and then is recirculated through that pump and into a filter cartridge that filters out small dust, such as chalk dust, so it doesn't come up to underwater whistles. On the wall behind there's a few other hydraulophone prototypes. You can see early prototypes. And underneath the workbench there, I've got a power supply from my childhood. It's an old Heathkit power supply, which I kind of like because it's got a nice big knob on it. So I do like that user interface, of really simple, large things. So this kind of thing here is just really nice to grab onto, like when you have a large knob like this, it's just a lot more satisfying to turn something like this old-fashioned. So I do like these antique power supplies and things like that for your user interface. It's actually a variable transformer on that one. The secondary of that transformer has multiple windings. And so I'll just turn that over to here and I'll play on that Nessie a little bit there so that you can see what that's like. I'm going to switch to the overhead camera and then I'm going to do a live picture-in-picture of this camera in the upper right corner so that you can see from the two different vantage points. Now, this is a fun example of a kind of piece of artwork, if you will. As I increase the voltage on that pump, the water comes out here more or less, depending on here. And then as I obstruct those finger holes, this is A, this is the letter A, is the first jet here. So let me know, can everybody hear that from the mic sitting on the table? Chat back to me, see if you can hear that. Okay. Like just type in the chat if you can hear that sound, all right? Okay, that's good. So now if I obstruct multiple jets at the same time, so C, E, and G, Then you have a C major chord. And if I obstruct C mostly, but you see I can also obstruct it a little bit. Okay, there's a little bit of G, a little bit of E, and lots of C. So there's C major with the emphasis on C. And then shifting the emphasis gradually, G. And there's F major with the emphasis on F. C major with the emphasis on E. G major with the emphasis on D. And back to C major with the emphasis on C. So I call it harmelody, the intertwining of harmony and melody. So we could just say, let's take a simple children's song like. And of course, as you vary the amount of flow, the less flow is quieter, so you can quiet here. As you increase the flow, get more sound level out. So hopefully that was a fun little introduction to some nice very nice sound waves propagation in water. The speed of sound in water is about 4.5 times faster than it is in air. And of course, when I was growing up, that was one of my inventions, was the underwater musical instrument, the hydraulophone. And of course, my kindergarten teacher said there's 3 kinds of instruments: strings, percussion, and wind. And was the kind of thinking was, well, you know, why is that solid, and gas? That's strings is 1-dimensional solid, percussion is like a 2-dimensional flat membrane solid, or a 3-dimensional bulk solid, and then gas. Air, wind is gas, so you've got like 1D solids, multi-dimensional solids, and gas. So what's the solid gas ontology or taxonomy? So I became kind of fascinated with ontologies and taxonomies and classification systems. And so then we have this sort of elementary organology of state of matter in which the sound is produced. So that led to this whole discussion around water as a medium for interaction. So anyway, on those happy notes, it's kind of a nice way to finish off, I think. And hopefully I'll see some of you soon to join in. Any of you are welcome to join us for a swim on Sunday and meet up, or in any case, I'll see you all on whatever day it is, if they stay with the 25th, or if it gets changed to another day, we'll check in and see. But anyway, we'll all meet up shortly, and I'm always open to help with the course, or if you need help afterwards with letter of reference or job hunting or finding your way around, or just general advice on how to get into the Silicon Valley community, or the MIT or Stanford community, or any of the worlds that I know, let me know, and hopefully we'll stay in touch and have some fun, and hope you all learn something and can apply this to making a better life and finding a better place in life. So on that happy note, we shall meet again soon.